Can start. Hello, I'm Shraddha from BITS Goa, and I'll be presenting my work on testing concurrent programs under relaxed memory models. Okay, so you might have come across situations in which you write a code and you get the desired output, but often after a while, if you run the same code, you get a different output. So why does that happen? The thing is, in a multi-threaded program, you can get different outputs for after different runs, because the way in which the threads are scheduled, that is quite random. And the main problem is often data races. So a data race occurs when two threads are trying to access the same shared variables, and at least one of the access is a write. So in this example, in event A, data is being written to X. In event B, the flag is set to indicate that the data is written, and event C is reading the flag which is set, and event D is reading the data from event A. Now, the forbidden condition here is that if R1 indicates that the flag is set and the data is ready to be read, then event D is still reading from the initial state. The initial state was 0. It should ideally read from the event A. The value here should be 1. So this condition is forbidden. Now, there are certain memory models like sequential consistency in which reordering of events is not allowed. So it can't happen that this will overtake this event. But there are certain relaxed memory models which allow reordering of events, and hence this condition might take place. So we need some software to test for these data races. Now, if we need softwares to test for relaxed memory models, why aren't we just happy with sequential consistency? Why do we need relaxed models? So the reason is CPU performance. Certain instruction reordering and out-of-order execution optimizations can't be done by only sequential consistency. So we need relaxed models. These are certain definitions. Read from indicates that the read R is reading data from write W1. In write serialization, if both the writes are to the same location, then W1 is write serialized with W2, means W1 happens before W2. And in from read, it's basically a conjunction of read from and write serialization. And happens before is an important relation between memory events A and B, in which if A is happening before event B, it indicates that the memory effects of event A are the thread which is executing event B, they are visible to that thread before B has happened. So let's consider this example. In this, thread 0 and thread 1 has 2 reads, and this execution can have a number of outcomes. So we'll be looking at this particular outcome in which R1 and R3 are 1 and R2 and R4 are 0. We suppose that there is a dependency relation between these 2 reads and these 2 reads, and if R1 is supposed to be 1, so it has to read the data from this event. So they have a RF relation, and if R2 is 0, it means it has read data from the initial state. So it is in FR with B. Similarly, if R3 is 1, it has to read data from F, and R4 is reading data from the initial state. So the goal here is to find out whether this execution has a cycle or not, and that is there for any execution, because if that execution has a cycle, then it's an invalid execution. So if we rearrange the terms, we come to know that this is one of the possible executions, and there is a cycle. Now, whether this cycle will actually occur depends on the memory model. Now, if we feed a program in our software, suppose, and TSO is one of the memory models, so it allows write to read order relaxations. So for TSO, that cycle will not take place because it does not allow particular reordering of events. So we get the output that all traces are good and feasible, and that execution is always valid. Similarly, for a PSO memory model, we get the same output. However, for RMO, since the read from maps are global, so we get this happens before constraint output. It's a conjunction of happens before constraints, which corresponds to the cycle which was detected before, and this indicates that because of these conditions, the execution is not allowed in RMO memory model. We also tackle the thin air problem. In this example, like before, there is a dependency between these 2 events, and we are trying to read, event A is trying to read from D and C is trying to read from B, so there is a RF relation. But here, since there is an XOR relation, this value is appearing to come out of thin air, because there's a dependency between them. So how did R9 even come? If like how can you read from here if R9 is not calculated? So this is the cycle, and we concluded that if RF union DP is acyclic, that means there is no thin air problem, and if it's not acyclic, then our software outputs the thin air constraints for that execution. So in summary, if we give a input program like this, we'll get the happens before constraints as output, and if thin air constraints are present, we'll get that also as the output. And the software does certain optimizations, like if A happens before B and B happens before C, then A happens before C is removed from the output.
Any questions?
Oh, yeah.